So at this point, you should have watched the video from the physics girl and figured out a little bit about standing waves. Now, one more time, let's recap the parts of a standing wave. A standing wave is when a wave reflects off a boundary. Imagine this wave is traveling to the right, it hits the boundary and reflects upside down. It then travels back in its original direction, but when it's trapped between two different boundaries, it ends up making a standing wave. It has reflection and interference to make a pattern of nodes and antinodes. Nodes are the part of the wave where it appears that no wave is moving. If I were looking at a string that was vibrating, this would be where the string stays still. There are four nodes in this picture. The antinodes, on the other hand, that's where the wave seems to move with maximum amplitude. If there were a bead on this string, this bead would start here and vibrate really rapidly up and down in place. There are three antinodes in this picture, and so we would call this the third harmonic. Another part of a standing wave is a wavelength, but this one I want you to pay special attention to. Notice that as the wave travels, it has an incoming wave, which I'm going to draw as a solid line, and a reflected wave, which I'm going to draw as a dotted line. The string only exists at one place at a time. The reflected wave isn't really there. You can see it in the demo and the experiment because the reflected wave is occurring so quickly that our eyes can't resolve it correctly. So when we want to draw one wavelength, that corresponds to one complete up and down of the string. It doesn't count the reflected section. So it turns out the wavelength isn't the length of one antinode, but it's actually the distance of two antinodes. In order to make one complete up and down, one wavelength has to be the length of two antinodes. So if I were measuring this wavelength, I would need to grab a meter stick or a ruler and measure the distance from the start of the motion to the end. Now let's see what that looks like in your lab for today. In your lab for today, either you'll be doing this in Pivot or in person. I want you to take a look at two trials. One with a high tension string. High tension would be high mass. And the other with a low tension string. Low tension, low mass. And what I would like you to do is take several measurements. On Pivot, you'll be restricted to only reading the first 6 patterns. But in person, there's an infinite number of harmonics you can make on a standing wave on a string. It might be useful to put these next to each other so it's easy to read your data. What I want to do is slowly increase the frequency by letting this play out. As it plays, the frequency of this oscillator increases until we get different standing wave patterns. This is the second harmonic, and I'm going to try and pause it right there. To read the frequency, I would read the number on the function generator. The frequency in this case is 20.7 hertz. So read the frequency off the function generator. I see that this is the second harmonic because there's two antinodes. So that means the only remaining thing I need to do is measure the wavelength. The wavelength is the distance of two antinodes. Hey, so coincidentally, the length of this string equals the length of two antinodes. So what I would do, pull out my meter stick, measure the distance of two complete antinodes. So this is about 100 centimeters or 1 meter. I read the frequency off the function generator. The wavelength is the distance of two antinodes. And the number of harmonics is equal to the number of antinodes. So if I let it play up to the last harmonic, I can see that this is the sixth harmonic because there's 1, 2, 3, 4, 5, 6 antinodes. I can read its frequency off the function generator. And its wavelength I would read as the distance of two antinodes from here to here. The only one I want you to be specifically cautious with is make sure when you do the first harmonic is a little bit troublesome because you actually can't see the whole wave. You only see half of the wave. Remember that wavelength is the distance of two antinodes. What you could do is simply measure the distance of one antinode and multiply by 2 to get the wavelength. So you would do this for all 6 trials at low tension and repeat it with the same chord at a high tension, high mass. That's how we do our data collection. For the rest of the graphs, in the conclusions, when you work on the graphs, keep in mind that these are sketches. You don't need to have perfect plots here. So what you could do is sketch the graph of number of harmonics versus wavelength and insert it in this position. This lab, experiment 9A, is due on Saturday.